Okay, Assalamualaikum dan salam sejahtera. So today we continue our discussion on our piston pump tutorial. So we go for example number 3 here. A single acting reciprocating pump has the following data. Stroke 300 millimeters, piston diameter 125, suction pipe 5 meters, suction pipe diameters is 5 millimeters. Okay, I'm sorry here. So, and suction pipe diameter is 75 millimeters. Oh, I'm sorry. Suction pipe length here is 5 meters. I'm sorry. So you assume this is the length of the pipe. Okay. And then suction head is 3 meter, atmospheric head 10.23 meters absolute, and safe minimum head is 2 meters absolute. What is the maximum speed at which it can be run without causing any separation during suction stroke? So the word separation here is actually when the bubble or the empty space start to appear or start to exist in the piston. So the empty space mean, I think you could imagine we have a piston pump here. So if the piston is pulled in high speed, very fast, you will find that there will be an empty space, mean a vacuum or a space where the liquid not entering the piston. So this is what we call the separation. Okay, because this will reduce the volumetric efficiency. At the same time, okay, will show that this pump is not efficient to transfer water. That's why we need to make sure that the speed of the piston is run at its considerate speed. So that's why in this question, they give you the safe minimum pressure head. So it is 2 meters absolute, means if the speed create pressure less than 2 meters, or mean piston speed is too high and it start to give pressure less than 2 meters, so means that that speed will create a separation, will lead bubble or leads air to flow inside that one, inside the piston space. So and then first we need to calculate the pressure head inside the piston pump. So in the suction, we know that the equation is atmospheric head minus with suction head and minus with acceleration head. So and then this is the equation for the acceleration head. So and then we focus at the beginning, as I said, because at the beginning this is a very critical point where we need to create vacuum, and that vacuum is the important point to make sure that water can be sunk into the piston bore. So and then we know that the cos omega t is equal to 1. Now the equation will become like this. So we substitute the value, so we get these terms. So when you substitute the value, we replace the value of omega here with 2 pi n over 60. So and then we could let the value of n here, RPM, remain as unknown variable. So we still have n by the square here. And then we substitute in this equation pressure head at the piston. So from the question, we know that the safe maximum minimum pressure is 2 meters. So we substitute in the equation, and then we could get RPM is around 47.38 RPM. And usually if you talk with engineers, sometimes they round up the value. So the rule of thumb for us to round out the value of RPM is, if the situation is less than 0.5 or more than 0.5, you are advised to round up to the next value. So mean if you get 47.38, you are advised to round up it to 48 RPM, whether it is less than 5, less than 0.5 or more than 0.5. Because when we reduce the RPM, for example, we take a 47.0 RPM, so it will make the piston is easy to clog. Means because we purposely reduce the speed, so means that the possibility to the machine to jam, to interfere each other is higher compared if we give more tolerance to the speed here. So that is for question 3. So means that you could imagine how a piston pump being the safety of piston pump being calculated. So we go for example number 4, a single cylinder double acting reciprocating. So now we are talking about the double acting, has a piston diameter of 300 millimeters and stroke length for 400 millimeters. When the pump runs at 45 RPM, it discharges 0.039 meter cube per second under a total head of 50 meters. So mean water will be transferred 50 meters above the inlet surface. What will the volumetric efficiency, work done per second, and power required if the mechanical efficiency of the pump is 75%? So the question asks to calculate the volumetric efficiency, work, and power, and so on and so forth. So first, we calculate the volumetric efficiency. So we have eta, the symbol for efficiency. So the equation is flow rate for actual divided by the flow rate for theoretical. So because we are double acting reciprocating now, so the equation become like this one. And then when we substitute all the values, so we get it is around 0.042417 meter cube per second. So please be remember that our equation here will give us answer in unit SI. So it will become meter cube per second. So I hope you could know how to convert it into liter per second. So 1 meter cube is equal to 1,000 liter. So and then we could compare the theoretical value with the actual value here. So we could find the volumetric efficiency. It is equal to 91.94%. So and then we could calculate the power. So the power is still rho GQH. So we substitute with the actual flow rate. And then from the question, we know that this pump will be used to transfer water for 15 meters. So we substitute the value of 15 meters here, then we get 5.739 kilowatt. So and then from the question, we know that the mechanical efficiency is 75%. So we use the idea of this equation, 0.75 power out divided by power in. Then we could calculate the power required for that pump is 7.652 kilowatts. So I hope you could relate this value with this value. So the simple meaning of this one is actually we need to supply 7.6 kilowatt power because 5.7 will be used to run the pump, and another 25% of this amount is actually need to overcome the friction and another resistance. So for example, in this one, we need to overcome friction that come from the shaft and from the crank and so on and so forth, that determined as mechanical efficiency here. So that is the example number 4, and then we go for example number 5 here. So let's say we have the following details of a single acting. So and then we have a single cylinder here and reciprocating pump, which is length of piston, mean the stroke is 500 millimeters. So the length of suction is 5 meters and the length of discharge is 15 meters. So we have the diameter of piston 1 to 5 millimeters diameter of suction pipe, and delivery pipe is 100 millimeters. And then it is given that atmospheric pressure is 10.2 meters. So the suction head is 3 and delivery head is 10 meters. So it is given that frictional factor for pipes is 0.02 for suction and delivery pipes, and the safety minimum head is 2.4 meters. So these safety minimum heads mean that we need to make sure that there are no separation occurs inside that piston. So, and then let's say we don't have any slip in this condition, and then we need to calculate again the maximum permissible speed and then the energy required to drive pump if an air vessel is provided on the delivery side, which is very close to the cylinder. So now in question 5, we start to calculate the difference between pipe with and without the air vessel. So first, this is the idea of the, we calculate the safety speed. So we start with the pressure head inside the piston. So because we are calculating the suction head, suction process, so the pressure head is actually the atmospheric head minus with suction head and minus with acceleration. And then you know the calculation of acceleration head can be simplified into this because we are calculating for the beginning stage. So the cos omega t is equal to 1. So we substitute everything. So we let the omega value is remain as 2 pi n over 60. And then we get this term with n square as the unknown variable. So we substitute the value of 2.4 as a safety head. So and then we could calculate the value of n, which is equal to 47 RPM. So and then we could calculate the power here. So and then to calculate the power, the equation is remain the same, rho g q and h. But at least I hope here in this question you could know how to determine the value of h. So and then we could determine that the total h that we need to calculate to substitute in the power equation is shown as this one. So the idea is to make sure that water can be transferred to the upper tank. Okay, we need to overcome height of the suction. So we call it as a suction head, and the height of the delivery. So we call it as delivery head. So and then we need to overcome the friction at suction and also the friction at delivery. Okay, so it is also reflect the diagram that we have in the in our previous lesson. So you could understand that why we need to overcome the suction head and delivery head, and why we need to overcome the friction that occur at the suction pipe and delivery pipe. So and then suction head and delivery head is quite simple because we could get that value straight from the diagram or straight from the question. So and now we need to calculate the value of friction. So because you know in piston they move in 3 major situations, which is the beginning, the middle, and the end of the stroke. So these 3 points will give us different value in terms of angle. So and then we will have 3 different value. So in this situation, because we want to only have one value to be substituted in the equation, so you are allowed to use the average value of the friction. So in the average value of the friction, so we use 2/3, F LS over DS 1 over 2G, and then we have A over AS. So A here is actually the cross-sectional area for piston divided by cross-sectional area for suction pipe. We have R omega square. So, and then if we substitute everything, we could get that the frictional head for suction pipe is 1.25 meters. Okay. So, and then we need to calculate the friction head for delivery pipe. But according to the question, it is found that we have an air vessel located nearby the delivery site. So means that if we have a piston here and near of this one, so we have the air vessel, and then the water start to flow to the upper tank. So the distance between this piston pump and this the air vessel is not mentioned, so means that we could ignore this length, okay, by the assumption of the length is not too long, so means we could ignore the friction that occurs in this section. So in this section, okay. So the problem, as I said previously, so if you have air vessel, the air vessel tank here will make your flow rate steady. So means that your calculation cannot be done using the idea of piston pump anymore. So you need to calculate the friction head according to what we learned in flow-in pipe. So we call that one the friction head for flow-in pipe is a major loss actually. So means that to calculate the friction head for the outlet here, so we need, please refer to the idea of major loss in flow-in pipe. We learned it previously, so I just describe it here. So you need to understand that you need to calculate the value of F, and then the equation will come F over d v squared over 2G. So they are not depends on the acceleration of the piston anymore. So it means that whether the piston is suck the water or deliver the water, the flow inside the delivery pipe is remain constant. Okay, so first we need to calculate the flow rate. So this is the flow rate that we have. So we have ALN over 60. So we get it is around 0.004795 meter cube per second. And please bear in mind that if you calculate flow rate for this subject, please calculate it until very detailed number. So might be it is not worth for you to get only 3 or 4 decimal, because unit of meter cube per second is quite large in terms of tolerance. So I mean, if you just lost 0.1 meter cube per second, it reflects about 100 liters per second that you not counted in your calculation. So please be careful. Might be the decimal point is not enough. You need to have certain consideration about the units. Okay, so for here, so we take 4 numbers here, 0.004795 meter cube per second. So, and then from the flow rate that we have here, we know that Q is equal to AV, and then we could calculate V is equal to Q divided by A. So we divide by the cross-sectional area for the delivery pipe. So we have the flow velocity inside the delivery pipe here is 0.61 meter per second. So now we need to use this equation to calculate the friction head in the delivery pipe. So we know that the equation for the friction or the major loss for a pipe can be written as this one. So, and then we substitute all the value. We substitute the velocity that we calculated earlier as 0.61, and then we could get it is around 0.0569 meters. So you could see here, so the losses for flow-in pipe, okay, so the length is 15 meters, it's around 0.0569 meters. So if we compare with our previous calculation, so this is the calculation of the friction head for piston pump. So the length is actually 5 meters. So we have the length is 5 meters, but we have value of friction at suction is 1.25. This is the comparison between the comparison of friction between the flow-in pipe and piston pump. So we found that in piston pump, the friction is higher. That's why people will install an air vessel tank after the piston pump, means at the delivery section, because we want to reduce the fluctuation of the flow rate. We want to make the flow rate steady, and then we want to reduce the friction, so means that it will give our piston pump more energy to transfer water. And we must know that at delivery pump, at delivery pipe, so length of delivery pipe is actually more longer compared to the suction. So normally it's suction is around 5 meters, for example, might be the delivery is around 20 to 25 or 30 meters. So the air vessel in the delivery pipe will reduce the friction loss in the delivery pipe. So according to this calculation, we get the friction for delivery pipe is 0.0569, and then we substitute everything in the equation, so we get the head. The total head is 14.3069. We substitute in the power equation, and then we get it is around 673 watt. So that is the calculation for the acceleration head, the mean calculation of friction in piston pump that has the air vessel. So we continue with the example number 6. Okay, so we have a single acting, single cylinder positive displacement pump is used to drain and excavation. So the pump has a bore of 150 millimeters and a stroke of 400 millimeters. The suction and discharge pipe are both 50 millimeters diameter. The suction pipe being 2 meter long, and the discharge is 6 meters above the level of the water excavation. The suction lift to the pump is 1.5 meter, while the discharge is 6 meters above the level of the water surface in the excavation. In the absence of any air chambers, so now we are calculating suction and delivery without any air chambers. A pump suction, B discharge, calculate for A and B, mean calculate the pump suction and discharge condition. The absolute pressure head in the cylinder, so we need to calculate the pressure head in the cylinder for pump suction and discharge. Okay, at the start and the middle of each stroke, if the pump drive at 0.2 revolution per second, so please be careful about these units, because it's already in second unit, so might be you cannot use the idea of 60 divided by 60, and maybe assume to be simple harmonic. So simple harmonic means the piston and delivery, the piston movement mean in suction and delivery condition, so it can be represented in harmonic graph like that one, or the graph will show in sinusoidal. So what is the graph? So at least the graph of flow rate. I think if you refer back to our previous notes, so I already show you the graph of this one, the flow rate. So means the flow rate is not it's not weird, so it can be shown, means your pump is run at a very good RPM cycle, so it's good suck water and deliver water in harmonic condition. And also determine the maximum pump speed if separation is to be avoided on the piston face. Assume a friction factor of 0.01, so this is the value of F. For both pipe, a pump slip of 4% and atmospheric pressure of 0.3 and of water, and a fluid vapor pressure is 2.4 meter. So this is the condition. So we have the suction pipe here. So we have the suction pipe. So the height is 1.4, the length is 2 meters. So the delivery pipe is 15 meter long. So the diameter is same here. And then by the height is 6 meters. And then you should know that this height is actually the total manometric height, mean the height from the input surface level and output surface level. So from this value, we need to calculate the delivery head, which is the 4.5 meters from the center point and the final, the output level. So, and then we have the stroke of 400 millimeters and the bore diameter, mean the size of the piston is 150 millimeters. So let's say we are going to calculate the absolute head. So this already discussed in previous question. I think I could a little bit faster here. So we could get the absolute head here by having the atmospheric pressure minus with suction head, acceleration head, and this time because we already know the friction, so we need to minus with the friction head for suction. So and then because the movement is in harmonic, means it can be represented by sinusoidal wave, sinusoidal curve. So we could assume that U is equal to R omega sine omega t. So you know about this, and our R here is actually half of the stroke length. So this is also discussed previously. So the relation between the diameter of the crank and also the total piston stroke at the piston pump. So and then we start with we have a three condition, which is the start, the end, and also at the middle stage. So the acceleration suction is okay. So we already discussed it previously. So this is the equation. So and then we could calculate it as at the beginning, the cos omega t is equal to 1. Then we have 0.579 meter as the acceleration head at the suction. So and then for the friction at the suction, okay, because we don't have any air vessel anymore, so we need to use equation, special equation for calculating the friction in piston pump. So this is the equation, and we cannot use the average equation, okay, because it is very specific at point where cos omega t, or the location where the omega t is equal to 0. So means that we need to use the equation of this one. So and then if we start to calculate, okay, so we will find that at start, so because the sine omega t is equal to 0, so and then the friction will become 0. So and then we get the total pressure head at suction at the beginning is 8.221 meters of water. So and then we could calculate the cylinder head at end of suction. So we substitute everything. So we get the acceleration head is minus 0.5 and the friction head is equal to 0. So and then we get 9.379 meters. So and then if we calculate at the mid stroke here, okay, so and then the acceleration head will become like this one, and finally we could get the at mid stroke the friction of suction is 0.104 meter. So now what we could do is, okay, we could calculate the total head at the suction. So it is equal to 10.3 minus 1.5 minus 0 and minus 0.104. So the total head is 8.696 meters. Okay, so until this one, I think you already know how to calculate the pressure head inside the piston. So means that you need to calculate both. You need to calculate all. So you need to calculate the suction head, you need to calculate the acceleration head, and then you need to calculate the friction head. So in suction, our main concern is we need to create enough vacuum strength. Okay, we make sure that the strength of the vacuum is enough to suck water from the input level to the piston. So for this one, okay, we need to calculate the absolute head in the cylinder during discharge. Okay, previously we are calculating absolute head in the cylinder for the suction. So I think it is already 2 or 3 times we calculate the pressure head or absolute head in the cylinder at suction. So what we need to do is we need to minus with all components that we have. It is because we must to make sure that the vacuum that occurs in the cylinder is good enough to suck to suck water from the input tank to the piston. So, but in discharge, we have a reverse idea. Means that for discharge, we need to make sure that our piston pump has enough power to push the water to the certain height. So, means what is the meaning of has enough energy means we need to make sure that the absolute head in the cylinder is enough. So the equation will become atmospheric head plus delivery head plus acceleration head and also plus the friction at delivery pipe. So because if energy or pressure cannot overcome all these parameters, so means that our water cannot be reached to the outlet tank. So please be remember the difference between suction and delivery is for suction we need to minus all the value because we need to create enough condition, and for delivery we need to add all of the parameters that we have because we need to create enough condition to push water to the desired level. So this is the calculation. So we have the atmospheric pressure is 10.3. So and then we need to calculate the delivery head, and please refer back to the diagram to the question. So we have 6 meters of the total height. So means that the delivery height is 4.5 meters because the suction, because the delivery head is actually from the middle point of the piston to the outlet surface, water surface. So the acceleration equation is like this one. Okay, so and then we substitute everything, we could get the acceleration head for delivery is 4.347. And then we could calculate the friction delivery. So again here, we cannot use the average value because we have the location, mean we have the amount of angle of the crank angle. So we need to substitute that angle. And then we cannot use the idea of flow in pipe, mean we cannot use the equation for major loss because there are no air vessel in this system. So and then if we calculate everything, we could find that the head, the absolute head at the beginning is 19.147 meters. You could show, you could find that this value is actually high enough to push water until its desired height. So at the discharge stroke here, so I make it a little bit faster. So we have 10.3, 4.5 for delivery head here, and then we have a minus condition for acceleration and the zero friction. So we have 10.453 meters. So and then for the mid discharge stroke, mean at the middle here, so we could calculate the friction is just 1, and we could get the total height, absolute head in the piston at the middle discharge stroke is 15.521 meters. So this is all the calculation for the absolute head in the cylinder in suction and delivery. So the idea is you need to understand that at suction, we need to minus with all the parameters, and for the delivery, we need to add with all the parameters. And now we need to calculate what is the minimum velocity that we could use for this pump before it's the minimum the maximum speed that can be used for this pump before without any separation. So in this question, they will give you that 2.4 meter absolute is the vapor. What is vapor pressure all about is, so let's say we have a piston here. So and then when your piston being pulled in higher speed, so maybe it's create an empty space like this one, for example. So means that this is all the water that sucked into the piston area, and we have an empty space here. So in this empty space, or in the first thought, is actually the vacuum. Okay, so and then what happened if we have a surface of water in a vacuum? So we found that there are molecules here that has tendency to be vaporized. So it will vaporize in this vacuum area, and it will create a vapor pressure. So that's why in this question they give us the idea of vapor pressure. So we substitute the value of vapor pressure here in terms of heat. So we have 2.4 meters. So and then we calculate, we could get omega square is equal 17.44, and then we could calculate everything is 40 RPM. Okay, so here I think you could understand that what we get here is actually the unit of omega. So the unit of omega is radian per second. So and then you need to convert the radian per second into revolution per second. So and then you need to convert into revolution per minute. So revolution per minute can be expressed as RPM. Okay, so means in this question, please be careful about the unit of the rotational speed. So and then this is the maximum velocity for pump to be operated without any separation. Okay, so means it is okay for you to run for this one, but separation will occur and it will reduce your volumetric efficiency.